This is section 4.3. So we are going to look at the multiplication rules and conditional probability. Let's look at the multiplication rules first. Multiplication rule says that if two events A and B are independent events, so you can take the probability of A and B, the probability of A and B occurring, which is given by just a product of probability of A and probability of B. What does mean by independent events? Look at the definition first. Two events A and B are independent events. That means A occurs does not affect the probability of B occurring. In other words, these two are acting like independent, right? The probability of one will does not affect another. Remember, in last lecture we had mutually exclusive events. So two events are mutually exclusive. That means both events cannot occur at the same time. But here, for independent events, they can occur same time, of course. But the thing is, the probability of one will not affect the another. So that's the difference between mutually exclusive events and independent events. Okay, so here we are going to use this formula. The probability of event A and event B will be just the multiplication of the probability of event A and the probability of event B. Okay, so simply you find the probability of A and the probability of B separately, then you find the product of those two. So it's going to be the probability of A and B. So let's look at this example one. A coin is flipped and a die is rolled. So basically there are two experiments are being done. Find the probability of getting a head on the coin and number 4 on the die. Well, before going to do this, ask yourself what are the events, two events mentioned here. So you could take event A as getting a head on the coin, and you could think of event B as getting number 4 on the die. Okay. Since the probability of getting a head on the coin does not affect getting number 4 in the die, because these two events are now going to be independent events, right? You are doing two separate things. Therefore, these two are independent events. Since these two are independent events, the probability of getting a head and number 4. So this is my event A. Getting number 4 is my event B. So the probability of A and B formula says that if these two are independent, simply the product of these two, right? The product of getting a head, then times the probability of getting number 4. Okay, so simply find these two probabilities separately, then just multiply those two. So that's the way to find the probability of two independent events product. Okay, so ask yourself, when you toss a coin, what is the chance of getting heads? Well, here there are two chances. You may have either heads or tails. So getting heads is a half chance, right? 10 times. When you roll a die, what is the probability of getting number 4? Remember, there are 6 possibilities when you roll a die, 1 to 6. So getting number 4, of course, only one chance. out of 6 possibilities. Okay, so the first fraction is coming from, the first probability, and my second is coming from the second one. So simply multiply these two, 1 over 2 times 1 over 6, which is 1 over 12. So that is the probability of getting a head, getting a heads on the coin, and getting number 4, on the die. If you want, you could be, done this problem in a separate way. Suppose if you want to find the total number of outcomes in your sample space for these two events, so let me denote my x-axis as the set of outcomes coming from tossing a coin. And let me denote my y-axis as rolling a die. So when you toss a coin, of course, there are two possibilities, two outcomes. You may have heads or tails. But when you roll a die, here I will have 6 possibilities. There are 6 numbers. So 1, 2, 3, 4, 5, 6. So that means if you consider these two events altogether, you may have how many outcomes? You may have 1, 2, 3, 4, 5, 6, and here also 1, 2, 3, 4, 5, 6. So in altogether, 6 plus 6, there are 12 outcomes. So if you want, you could list them, So my possible outcomes in my sample space is getting heads from, coin, and this is my first, you could take this as your first outcome, when you consider these two together. So this point will say that you are getting heads in first, touching a coin, and you are getting number 1 from rolling a die. So these all together considered as one outcome. Then if you look at my second one, getting heads and the number 2. Another possible answer, getting heads and number 3, and getting heads and number 4, getting heads and number 5, getting heads and number 6. Or you may have, getting tails on the coin and getting number 1 in, from the die, or T and 2, or T and 3, T and 4, T and 5, and T and 6. Okay, so if you do 2 experiments, you have to consider those 2, as a one outcome. So this is my one of how many outcomes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 outcomes in total, right? Out of 12, this is one of those, getting heads and number 1 from Jai. So I'm listing all possible outcomes, right? So the question is here, finding heads, that means H from your coin, and number 4. So where is that? That is here. So you have only one outcome out of 12, right? Therefore, getting heads means H, and number 4 is, of course, I have only one outcomes out of 12. So this is another way to do this problem without using the formula. So I have explained this in different way. Okay, so you could think of the second method of doing this problem without using that the independent formula. So I did not use the formula here, so this is the separate thing. So you could and make sure that you get both of the ideas. Okay, right. So now let's move to a second example. A card is drawn from a deck and replaced. So you are drawing a card and looking at what type of card you got. Then you are replacing and you are taking one more card. Basically, you are doing 2 set of experiments, probability experiments, but you are replacing the card, right? That means second chance, when you draw a second card, that probability, you know, will not be affected by the first drawing because you are replacing the cards in both experiments. You will have same number of, possible outcomes. Therefore, those two events are considered as independent events, right? So getting first card and getting the second card, these two events are now independent events. But if you draw one card and if you are not replacing and choosing the second card, now the probability of second card, whatever you choose, will be affected by your first card, right? Because you are drawing first card and not replacing. So in second time, your possible outcome is now different. First time you had 52 cards, now you have 51 cards. So you see now two different probabilities now you will have. So that is there. So when you replace the card, so two events are going to be dependent events. Okay. So when you replace the card after drawing, it's going to be, the second time when you draw a card, it is going to be independent event. But if you are not replacing, keeping out, then it is going to be a dependent event. Okay. But here we could use the formula, product rule formula only for independent event. Therefore, make sure that two events are independent when you apply that product formula for two events. So now here, since you are replacing the card, so let me write down here, when you replace, a card, this, when you replace a card and drawing the second card, so this is considered as independent events. Independent events when you do not replace, keeping out, and drawing the second card. Okay, these two events are now going to be dependent events. So make sure that you understand these two. Okay. Okay. So now let's look at the problem. A card is drawn from a deck card and replaced. Then a second card is drawn. Therefore, independent event. Independent event. Find the probability of getting a king first time and then getting number 7 from second time. So the probability of getting a king from your first drawing and then getting number 7 from your second drawing. So you could think of getting a king is as your first event A, and getting number 7 is, you may think like event B. So you are using probability of A and B formula. Since these two are independent events, so you could use that previous results, that is simply PA times PB. What is PA here? PA is nothing but the probability of getting king from your first drawing, then the probability of getting number 7 from the second drawing. So the getting a king, remember there are 4 of them in your card pack out of 52. There are 4 kings. Each shoe has one king. The probability of getting number 7, again there are 4 sevens in your card pack out of 52. You see now the number of outcomes in your sample space for both events are going to be 52 because you are replacing the cat. The number of cats will be same for both experiments, right? So now simplify these. When you simplify these, this should be 1 over 13 times 1 over 13. It is 1 over 169. So if you round up these to the decimal number, it is going to be 0.006, 3 decimal places. So you could leave your answer as a simplified version of your fraction, or you could round up into three decimal places. Okay. Okay. Let's look at example 3. An urn contains two red balls, five blue balls, and three white balls. So there are two reds, five blues, and let me call BL as blues, and three white. So in total, I have how many different colors balls here? There are 10, right? So there are 10 balls. So we are selecting one of those, and we are looking at what color we got. Then we are replacing and getting second one. Therefore, since you are replacing, two events are now again going to be independent events. So it is independent event problem. Okay. So what are the questions now? The question was there are a couple of probabilities you need to find out. So let's see one by one. So if you think of this is a given urn, so selecting three blue balls. That means uh, we need to consider as three consecutive probability experiments are done. So the probability of three blues, that means this is first time blue and second time blue and third time also blue. So this is the meaning of getting three blues, right? So now I have three events A, B, and C. My event A is here getting a blue ball in my first attempt and getting blue ball in second as B and getting third one is in my event C. Since you are replacing every time, these all three events are now independent events. Therefore, the probability of finding end is going to be simply the product of all three separately, right? Find all three probabilities A, B, C separately, then find just the product of those three. Okay, right. Now ask yourself, what is the probability of getting first time blue? Simply you are drawing one ball out of 10. So what are the possibilities of getting blue? Well, there are five possibilities because five of them are, in urn. So it is 5 out of 10. So when you, draw the second ball, remember you are replacing whatever you got first time. So again, in second time also, you will have 10 possibilities. So now second time also getting blue is again 5 over 10. Even for the third time also 5 over 10. So this is the probability of getting three blue balls. So this is next. So when you simplify this, take your calculator if you want and simplify. So you should get this is just half times for each, right? Half times half. It is 1 over 8. Okay. So now let's move to the second one. Let me do somewhere here. Selecting one white ball and then a red. Selecting white and one white and one red. So you could think this as your event A and this is event B. Since these two are independent again, so this is simply the probability of product of A and B. So the probability of A is getting white ball. Remember, there are three of them, so it is 3 over 10 times getting red balls, that is 2 out of 10. So it's going to be this is 1 over 5, so it's going to be 3 over 50, right? Okay. Let's move to number 3. Selecting two blue balls and then one white. So selecting first two is blue and third one is white. That means what? That means The first attempt you are getting a blue, one blue, and second attempt again one blue, and the third one is going to be one white. Remember now, you are going to do again three consecutive probability experiments. Since all three are independent events, you could simply find the product of all three. So first blue, then times the probability of second blue, then times the probability of third white. Okay, getting first blue is again 5 out of 10. So you are replacing for the second time. Again, you will have a 5 over 10. But for the third time, you are looking for a white color. So it is going to be 3 out of 10. So then simplify this answer. So this is going to be half times half, 1/4. So 1 times 3 over 40. Okay, let's look at the second definition here. When the outcome or the occurrence of the first event affects the outcome of the second event, in such a way that two probabilities, the way of the probabilities now change. These events are, dependent events, right? As I said earlier, the probability of one will affect another. Okay, so look at these set of examples for being dependent events. Drawing a card from a deck, then you are not replacing, and then you are drawing a second card. So these two events are now going to be dependent events, right? You are not replacing. Selecting a ball from an urn, not replacing again, and then you are choosing the second one, again going to be dependent events. Being a lifeguard and getting a suntan, yes, these two are related, so it's going to be dependent. Having a high grades and getting a scholarship, yes, of course, if you have a high grade, so the chance of getting a scholarship is high. So there's a connection between these two. So whenever you have, the effect of getting the scholarship is based on your grades. Therefore, these two are considered as dependent events. Parking in a zone parking area and getting a parking ticket. Yes, of course, these two are now connected, so it's going to be dependent events. Okay. So when you have a dependent event case, now you can't use earlier formula for two probability end. So we should have some other technique to find two probability. In that case, we are going to use the conditional probability technique. What does mean by conditional probability? Conditional probability means, suppose if you want to look at the probability of any event B, but if you know that's an event A already happened, occurred, right? So you are doing the second experiment followed by the first experiment, so already, already done. Then those type of, the probability of an event called as a conditional event. Conditional on what? Conditional on previous event. So we write like that: the probability of B with the slash, and the event already happened second. Okay. So how do you read this? We have to read like the probability of event B, right? Conditional on event A. Okay. So basically, we are looking for the event B probability. So this is our task. Okay. But we are imposing the condition. What is that condition? So we already know that event A is happened, right? Okay, if this is the case, then the probability of A and B. So remember, now here you have to consider A and B are dependent events. If two events are now dependent, then the probability of A and B is given by what? The probability of A and B is simply the product of probability of A then times the probability of the conditional probability of B given A. Okay, so now you see this is the difference between your conditional, your dependent formula and independent formula. In earlier we had here just P of B. Now instead of P of B here we have a P of B given A because of the conditional. Okay, so when you perform kind of problems with A and B probability, ask yourself whether A and B are independent. If it is independent, use the first formula we learned. If it is dependent, then use the conditional related formula. We will do some examples, then you will understand. Okay, so this is going to be example 4. What is example 4? 3 cards are drawn from an ordinary deck and not replaced whenever you are not replacing, so it is going to be always a dependent event. So getting a probability of one event definitely will affect another. So find those probabilities. So let's do this. Okay, so I'm going to do somewhere here. First one. So we are drawing. So the first one is finding the probability of getting all 3 jacks. What does mean by that? That means first card is a jack, and second card is jack, and the third is also a G. So now this means let's find one by one. What is the chance of getting jack in first drawing? Remember, there are 4 of them out of 52. But now, what is the chance of getting second one is jack? Remember, you are not replacing the card for the second time. So second time I have 51 cards now. So remember, first time you already have chosen jack, therefore we will have left over only 3 for the second time. Again, you are not replacing for the third time. Third time you will have only 50 chances. So you assume that you took two jacks in first previous 2 attempts. Therefore, third time you are having only 2 out of 4. So that means you simply multiply all 3 possibilities. Okay, but remember, unlike independent problem, in independent problem you will have same number of outcomes every time. But now not same, right? Because the number of possibilities are now getting smaller and smaller. So this is because of the conditional probability. Okay. So now this is the answer for the first one. So if we simplify, you should get. Okay, let's move to the second one. The second one, what is the probability of getting an ace first time, the king in second time, and queen in third time? So therefore, the probability of first is, and the second one is king, and the third card is now a queen. Simply you just find the probability of first time getting an ace. So what is the probability of getting that? Ask yourself. So what is the probability of getting ace in the first attempt? Remember, there are 4 aces in your card pack, so it's going to be 4 out of 52. Okay. The second time, what is the chance of getting king? Okay, you are not replacing, so you will have only 51 possibilities. Remember, you assume that first time you choose ace, so that means in the second time all the kings are going to be inside. Therefore, there are 4 kings already there in the card pack, so you have 4 possibilities. But the third one, again, you are not replacing, you will have 50 cards left over. Out of 50, how many possibilities are there to get a queen? So first two attempts, getting ace and king, so all the queens are again inside. So therefore, it is 4 out of 50. Okay. So now simplify these. If you simplify, you should get these as um, h over 16,575. So if you round up this answer to the decimal place, it's going to be four decimal places, 0.0005. Very small probability again. Now, if you look at number three, what is the probability of getting a club first time and spade in second time and heart in third time? Okay, again, getting clubs. You remember there are four suits in the card packs: spades, clubs, hearts, and diamonds. There are 13 of them. So, getting a club in your first attempt is 13 possibilities. You may have any of those, you know, out of 52 times. Remember, for the second time, again, I have only 51 choices. Out of 51, how many spades are left over? Remember, in first attempt, you choose only clubs. All the spades are going to be still there. Therefore, 13 of them. And in the third, attempt, I have again 50 left over. All the hearts, varieties are there inside. Again, it is going to be 13. So only the denominator will keep on, decreasing because of you are not replacing. So now when you simplify this answer, sorry, when you simplify this answer, you should get 169 over 10,200. So if you round up this to three decimal place, you will get 0.017. Okay, so make sure that you are getting these numbers correctly. Number four, getting all three clubs. Getting all three clubs. That means first row getting clubs and second time again clubs and third time again club. All three clubs. So when you choose first time, of course, there are 13 clubs out of 52. But remember, second time, you will have only 51 chance. But remember, you already choose one club from the first attempt. Therefore, you have only 12 left over. Then again, the third one, only 11 left over out of 50. So if you simplify this should give you 11 over 850. So that is nearly 0.013 to two decimal places. So this is all about the conditional probabilities. Okay. You see now why it is conditional. For instance, look at the second answer here. The second answer depends on your first answer because of first you choose already jack. The second one now is going to be reduced, right? So it is kind of condition. Okay. Now let's look at. So I'm leaving this one as just to practice. Oh, problems. You could practice those problems. Okay, let's move to the conditional probability formula. The probability of the conditional, probability B given A is nothing but the probability of A and B then divide by P of A. Okay. So this is the formula we are going to use for the conditional probability. Okay. So now let's look at this example. So example number, this is going to be number 5. This is going to be number 6. A box contains black chips and white chips. A person selects two chips without replacement. So he's choosing two chips one by one without replacement. So therefore this is a dependent problem. So we have to use the conditional probability anyway. If the probability of selecting a black chip and a white chip is given. So let me recall the as choosing a black chip and let us write W as white chip. So the given probability 5 over 56 is, the selecting black B and a white, selecting B and a white. So this probability is now given 15 over 56, and the probability of selecting a black chip, right? The probability of selecting a black chip on the first row, this also given 3 over 8. Then what is the question? Question is find the probability of selecting. The question is find the probability of selecting white chip on the second row, given that we have already chosen a black chip from the first attempt. Okay, so that means indirectly they are asking us to calculate this guy, right? The probability of white given B. Formula says that y given b, if we apply that formula, instead of b now I have w, and instead of a I have now b. I'm using that conditional formula. The probability of w given b is nothing but the probability of w and b over the probability of choosing black. Okay, so now these two are given, straightforward. These two are known. You see here. So the probability of B and W is the same as the probability of W and B. So that is going to be 15 over 56. That is going to be my numerator probability answer. Divided by the denominator probability is P of B. P of B is 3 over 8. Okay. Simply, plugging the correct fractions in proper place will give you straightforward answer. Now, if you simplify, you should get this as 5 over 7. That is 0.714. So you need to put the correct, fractions. Otherwise, you may end up with the answer which is bigger than 1. So remember, you are finding the probabilities. So probabilities cannot exceed 1. So therefore, make sure that you are getting an answer always less than or equals to 1. Right. Let's move to example. This is going to be example 7. Sorry for the typo. And this is 8. And example 7. The person selects 3 cards from an ordinary deck and replaces and each card after it is drawn. Find the probability that the person will get at least one heart. Okay. So first of all, if you have kind of word problems, so it is always easy to change the given problems in symbolic way. So what is my problem here? You need to find the probability that the person will get at least one heart. Okay, so I'm denoting that event as my event E. Event E is nothing but getting at least one heart. So read the problem carefully and define the given event by the alphabetic letters. It's always going to be easy. Now this is my question part. The question part is find the probability that the person will get at least one heart. So if you change this entire problem in terms of symbolic way, that is nothing but they are asking us to find P of P, right? Okay. So I'm going to use, the complement event we already have discussed in previous sections. So the question is now finding the probability of getting at least one heart. Remember, he is choosing 3 in a row. Okay. So I'm going to use the complement event technique. If my event E is getting at least one heart, so remember he has to take 3 cards in a row, then what is my complement event E bar? Remember, E bar is the negation of your event E, right? Statement. Negation of the given statement. The given statement is getting at least one hat. Then what is the negation of at least? So getting at least means he may have at least he has to get one hat means he may have the chances, right? So let me write down here the chances. Chances are he may have one hat or maybe two hats or maybe three hats, right? So now the at least one, what is the complement of at least one? None of them, right? So the negation, in other words, the negation of getting at least one means, you know, the outside of these, outcomes. So that is going to be, the none of them. So that means zero hearts, right? So that is the meaning of, the negation, right? So the negation of at least one is going to be none of them. So that means I'm using the complement formula we already have. The probability of E is given by 1 minus probability of E bar, right? So I'm using this formula. What is E here? E is getting an at least one heart. So the probability of getting at least one heart is nothing but 1 minus the probability of E bar. E bar is none of them. None of them is heart. Now finding this probability is easy. Why I am changing into complement? Because of finding a straightforward answer is kind of difficult. That's what I'm changing the given problem in terms of complement. Complement will make always easier. So now what is the meaning of none of them is hard? That means in all three atoms he is not getting the heart. That means the probability of none of them is hard means the first choice is non hard, right? And the second chance also, the non hard. And in third drawing also he's not getting hard. So that's the meaning, right? So finding these three probability is now much easy. What is the probability of getting a non-hard? First attempt. Remember, there are 13 of them are hards. The remaining all out of 52 are going to be uh, non-hard. Therefore, this is 52 minus 13 is going to be what? 39. So this probability is 39 over 52. Remember, he is replacing all the cards, right? Therefore, it is simply the independent event. So the second time also you will have a 39 out of 52, and third time also 39 out of 52. Okay, then if you simplify this is 27 over 64. So changing the problem into complement is always will be easier, much easier than dealing directly with the given problem. Whenever you see the word at least, at most, then you could use the complement of that event to make the problem much simpler. So without changing also you would have done this problem, but it will have more work, that's what I'm changing into complement. So if it is at least you need to check all three cases one by one, so you will have kind of a complicated way to do this directly. But once we change this into complement event, that is easy. We all know for sure all three atoms are no hearts. Therefore, it's always easy to find out those three easily. So that's why I'm changing. Okay, so if you simplify this, you should get 1 minus, if you plug in this into calculator, you should get 27 over 64 and this should give you 37 over 64. So it is always easy for us to change the given problem into complement event rather than doing directly with E, because if you want to do this problem, without changing, complement, that means you need to look at three possibilities, right? So at least one heart means he may have one heart drawing, or two hearts drawing, or three hearts. So you have to consider all three separately, and it's kind of complicated. So that is why I'm changing, the given problem into complement. Once you change into complement event, it's very easy now. We know for sure all three atoms are, not having any hearts. Therefore, all three atoms should be, non-heart problem. So it's easy to find one by one. So that's what I'm changing the given event into complement event. Whenever you see the word at least or at most, so it is always easy when you change this into complement event. Okay, so the problem will be much simpler. That's why I'm changing. So now look at next example. A single die is rolled four times. Find the probability of getting at least to 1/6. So you are drawing uh, you know a die, rolling a die four times. So out of four attempts, they are asking you should have at least 1/6. So what are the the possibilities? So the question is now finding the probability of at least getting 1/6. Like earlier, you could denote this as event E. If this is event E, right? So then what is my complement event? Getting at least 1/6 means the complement of E is going to be none of them. So none of them is 6. So you are not getting 6 in all four attempts. That's the meaning. But formula says that P of E is 1 minus P of E bar. That means what? That means the probability of E bar is none of them is number 6. Remember, you are rolling a die four times. Okay, that means the probability of first time no 6. That's the meaning. And second time no 6, and third time no 6, and the last time fourth attempt also you are not getting number 6. So now remember, rolling a die is a dependent event, so you could simply find the one by one and take the product of all four. So then ask yourself, what is the probability of getting, uh, you know, no 6 in your die? Remember, there are six possibilities. Of course, one of those six possibilities is getting number 6, but getting number 6 other than, getting number other than 6 is going to be 5 chances out of 6. In second time also 5 out of 6, 5 out of 6, and 5 out of 6. So getting number other than 6 is 5 chances out of 6 for each trial. So therefore it is 5 over 6 times 5 over 6 times, so 5 over 6 times 5 over 6. So when you simplify this, should give you 0.518. Okay, last problem. The American Automobile Association reports that of the fatal car and the track accident, 54 chances are caused by a car driver error. So that means the probability of getting an accident by you know caused by a car driver. So the accident caused by the car driver is given, which is 54 percentage. That means if you divide this into 100, you will get that 0.54 in decimal place. We know that probability. The probability of car driver error is 0.054. Now the question is, the first part, if three accidents are chosen, so you're choosing three accidents randomly and checking what was the cause of those, the fatal accidents, right? So the question is, what is the probability of getting all three accidents are caused by a car driver? So all three accidents caused by car driver. Remember, now you are checking three accidents. All three accidents are having different, independent records, right? So you could think of all three independent events. So this is nothing but you just checking three accidents. So that is nothing but the first accident and second accident and the third accident product, right? So this is nothing but uh, the probability of the first accident caused by car driver and the second again car driver and the third accident also caused by car driver. So what is the chance of having these probabilities? Remember, all three are now independent. Simply take the product of all three. So remember, we know the probability of getting car driver chance is 0.54 for each time. Whenever you check, the probability of getting the accident caused by car driver is 0.54. But I have three of them, so simply you just multiply. You know, so that is the probability of first part answer. So if you simplify, you should get 0.157. Okay. The second part, the probability of none of them is caused by a car driver. Right? That means what? That means you are checking three accidents. The first accident caused by a non-car driver, and the second accident also non-car driver, and the third one also non-car driver. Therefore, all three are again independent events. Simply multiply those three. But remember, the probability of the making car driver error is 0.54 means 54 percentage. So remaining 46 percentage is caused by non-car driver, right? That means the probability of a non-car driver caused by an accident is 0.46. The remaining leftover from 100. So that means that probability is not 0.46. Therefore, the first accident for being a non-car driver is of 0.46, and the second one also 0.46, and third one also 0.46. Okay, so simply simplify these three. So you should get 0.097. Please make sure that you are getting my answer. And the last part, the probability of getting at least one accident is caused by car driver. Okay, remember in previous example I explained you, if, if you think this event as E, then it is always easy for us to write this in complement formula. The probability of E is 1 minus P of E. If my event E is at least 1, that means my complement event of at least 1 is none of them. So none of them is caused by car driver. Okay, that means what? You are checking three accidents in a row, all three caused by non-car driver. But that answer already we have in previous part, right? So none of them is caused by a car driver. It is the answer we got in part B here. So you don't need to do the problem again here, but you know the answer of, the probability of none of them is caused by car driver. So simply plugging whatever you got answer from part B. So I'm simply plugging that answer because this this is the answer I got from the part B. Simply plugging those answers. 0.097. So simplify this. So you should get 0.903. So this is a high chance probability, right? So this is all about finding the probability with complementary events. Okay. So these all exercise should be a little bit harder for you guys. So I just want you to understand. And if you have any questions, so please let me know.